Hello and welcome to this course. I am Dr. Sriram Kumar. Today we are going to learn carbon nanotubes and their applications. So in this class, we are going to learn what is carbon nanotubes, what are key and important properties of carbon tubes, and based on their properties, where we can use these carbon nanotubes, that is application of carbon nanotubes. And then after, we will learn the important methods of carbon nanotube synthesis. So we will learn three different techniques. One is arc discharge method, second is laser ablation technique, and the third is chemical vapor deposition technique. Though I already explained these methods of nanomaterial synthesis in the synthesis part, but again I will explain in more details for carbon nanotubes synthesis. So now let's first understand what is CNT. So whenever we think about the CNT, we should start with graphene. So here we have graphene sheet. This is monolayer of the graphene. And you can imagine graphene sheet is kind of the single layer of graphite. So if you have the 3D material of the graphite, and when you take single layer of that graphite sheet, so that becomes graphene. And once you have this graphene sheet, and if you just roll that CNT, suppose you have this is graphene sheet, and when you roll into the cylindrical kind of the structure here, so that becomes here CNT. So here, if you just roll up, so that becomes CNT, and that CNT depends on the whether you have single wall CNT or maybe you have multi-wall CNT. So that depends how many CNT graphene sheet you roll up and make the CNT. The interesting point is that so that the synthesis of the CNT was kind of the incidents. You can understand that because the scientists were synthesizing fullerene. So scientists were synthesizing this fullerene using graphite. However, they found that under the steam study that graphite becomes as the carbon nanotubes under the electric discharge method. And then after, the scientists were also working on those fields to improve the overall the synthesis process of the CNT. So if you want to define CNT, so we can say that CNT is kind of the cylindrical structures of graphene sheet, and that has the hexagonal lattice. And each carbon in that CNT is sp2 hybridized as in the graphene. So this is about the CNT. So if we just understand rolling up the graphene sheet into the cylindrical structure is called the CNT. So we need to know whether how many CNT molecules we have. So we have either single wall CNT. So this is example of single wall CNT, or maybe we have multi-wall CNT. And we have here this multi-wall CNT. So in the multi-wall CNT, we have this concentrated cylindrical structure, and each cylindrical structure we have the diameters is bigger and bigger and bigger one. So if you have the cylindrical kind of structures and you have the smaller one, then bigger one, then bigger one, and then bigger one. So this is, and that is the example of multi-wall CNT. So if you want to understand how to make single wall CNT and the multi-wall CNT, so we have a structure. So if we just start with single layer of graphene and you just roll up, so that becomes single wall CNT. However, if you have this multi-layers, if you have 2, 3, 4, maybe the 5 layer of the graphene sheet, and if this roll up, so in this case, you have kind of multi-wall CNT. So that is the only difference between the single wall CNT and multi-wall CNT. And if you want to know the structures, so here, so let's start with the graphene. So here in the graphene, so each carbon is sp2 hybridized, and the carbon-carbon is in the covalent in nature. So if you just roll up, so here the diameter of single wall CNT is from 0.2 to 2 nanometer range, and here the length of this tube is from 0.2 to 5 micrometer. However, in this multi-wall CNT, so the diameter is from 2 to 100 nanometer. And the important thing is here is that here in multi-wall CNT we have the many concentric cylindrical structures, right? So the distance between the one layer to other layer of the cylinder is 0.36 nanometer, and maybe we can say 3.6 angstrom. So that is the interlayer distance between the CNT layer in the multi-wall CNT. So if you want to understand what is single wall CNT, so okay, so single wall CNT has a diameter close to 1 nanometer, and here is the band gap is used to 2 electron volt. So that depends on whether that CNT is metallic in nature or maybe semiconductor in nature. So it depends on that. At the same time, that electrical conductivity also depends on whether that kind of CNT is metallic or maybe semiconductor in nature. And this is kind of the scanning tunneling microscopy of the single wall CNT structure. And in multi-wall CNT, we have the concentrating layer of the CNT here. And based on that, we have the interlayer distance is 3.4 angstrom or maybe 3.6 angstrom. And here, there are two kinds of models we can use to explain multi-wall CNT. One is model is the Russian doll model, and second is the Perchment model. So let's understand the Russian doll model first. So here in the Russian doll model, we have kind of CNT rolling. So if we have the CNT and that CNT has the diameter. So in this kind of the CNT, we have the concentrated. So we have the a smaller diameter, then bigger diameter, and then bigger diameter. And that is kind of here we have the concentric cylindrical structures, and that makes the Russian doll model. However, we have the Perchment model. So if you want to explain the Perchment model, so we have CNT sheet here, and if you just wrap that CNT into like the paper folding here, if you just fold this one like this way, so here we have kind of the structures, and that structure, the folding, kind of the folding is called the Perchment model. So we have two kind of nanotube. One is Russian doll model, and second is the Perchment model. Okay, so till now we understand what is CNT and how many types of CNT we have. So now let's learn these properties. So first properties is about the atomic arrangement. Since that CNT may be either single wall CNT or maybe multiple CNT are made of the graphene, and the graphene has hexagonal lattice here, and at the same time it has the sp2 hybridization. So in CNT also each carbon is sp2 hybridized, and the structure lattice is hexagonal lattice in the CNT. And the second kind of properties is the scalability and the diameter. That is really important properties of CNT. So here, scalability. So scalability we can explain in terms of the kind of folding of CNT. So here we have sheet here, and if we just fold CNT to make the cylindrical structure, so based on the kind of the folding, or maybe the locking, after this folding you have this kind of locking, right? So based on that folding mechanism, we have three different kind of CNT. So now let's understand one by one. So I'm not going in details about these vectors. So that is unit vectors and there's integers here. But let's understand in a simple language is that if you just fold CNT, graphene to make CNT, so based on this here the kind of the connections, we have three different kind of scalability. We have the armchair type of CNT, maybe we have the zigzag, or maybe we have the carrel CNT. So here, so in armchair, so if you have these two vectors, N and M vector, so if we here in armchair, if you have the both vectors are equal, so we both are equal. So in armchair, we have kind of the arm, kind of the structure there here on this closing point. So because of this kind of this locking and closing, we can define this one is the armchair. And we have another kind of this closing that is zigzag. So in the zigzag, we have here n not is equal to 0 and m is equal to 0. So we have this kind of locking. And we have the another kind that is carrel kind of here with on. So m not is equal to m. And this is the m and kind of this locking these, closing there. And based on this closing vector, we have three different kind of CNT. One is armchair, zigzag, and the straddle. And based on this one, this scalability, we have different electrical properties of CNT. For example, those all armchair locking, the armchair CNTs are in the metallic. So if you want to use metallic CNT, so we need to always go for armchair locking of this that graphene. That is the armchair that's metallic in nature. And the zigzag and most of the scalar CNTs are in the semiconducting nature. So it depends. Suppose you are looking for the semiconductor application, maybe a metallic application. So based on your requirement, you can either choose armchair CNT, maybe the zigzag CNT. And that is very important properties of CNT. And now let's understand mechanical properties. Here, CNT has tensile strength that is maybe close to 100 times more than the steel. So now let's just compare in this table. So we have this modulus here, we have the tensile strength, and then we have here the steel and the CNT. So we just compare this data. So we have the tensile strength for CNT multi-wall and the single wall CNT is close to the 100 to 200 range. And for the steel, we have this value 1.3. So here it is close to the 100 times stronger as compared to the steel here. And you just compare here this modulus here 210, and so as compared to 210 it has Young's modulus for CNT 1000, so it is 5 times more as compared to the steel here. And if you just understand the density of the steel and the CNT, so the steel has density is 7.8 gram per centimeter cube, and the CNT has 0.7 to 1.7, so it is close to 10 times lower as compared to steel. And that makes the CNT is very important. That has this, that is stronger, at the same time it's lighter. So you can use that CNT for the diverse application. And at the same time, because of that exceptional strength of the CNT, we can use these structure because it can absorb high energy and resist factors. And next important properties of CNT is electrical properties. And based on the kind of the closing of a graphene to make the different kind of CNT, armchair, zigzag, and spiral, we have either metallic properties or maybe the semiconducting properties. And based on the dual nature of properties, we can use this material into the nanoelectronics application. Now, let's compare the conductivity of CNT with the copper or maybe some gold here. So we have this copper, and that copper has conductivities close to the 6 × 10⁷ Siemens per meter. And here we have the conductivity for single volt CNT and multi-volt CNT. So it is really very close as compared to the copper, right? And for this is the gold, silver. So here the conductivity is in a similar order as compared to the metal, for example, copper, gold, or the silver. And the second important property is the ballistic transport. So ballistic transport means that so there is the conduction of the electron from point A to point B, right? And CNT has the hexagonal structures. So if you want to transport an electron from point A to point B, so because of this ballistic transportation nature, the connectivity, the connection of the electrons is very high from point A to point B. And the second important point is that there is no such kind of the scattering of electrons. So here, no scattering of electrons. And that is very, very important point. If you have a CNT and if you are just transporting electron from point A to point B, and if there is no scattering happens while it's traveling, that makes very important features, and based on that we can use in an electronics application, and that is the properties is the ballistic transport application. And the third important point is about quantum effect. Because of the confinement in 1D kind of a structure, we can have the we can use in the transistors, sensors, and other electronics devices. Okay, now let's understand conductivity, thermal conductivity. So if you want to understand the thermal conductivity of CNT with this copper, so here we have the very high thermal conductivity of CNT as compared to the copper. Here, if this compare here, the copper has values close to 400 and the CNT has values more than 3000. Right, so it's very high thermal conductivity as compared to copper. And if you just understand anisotropic heat transfer, so anisotropic heat transfer, and let me explain one important key point here as well. So here the thermal conductivity is very high along the axis of the CNT. So you have CNT and this axis is this directions, right? So you have CNT here. So here the thermal conductivity is very high along this axis. But it's thinking about the thermal conductivity. So if we have the second CNT here, so what is the heat transferred from CNT A and CNT B? So here there is very poor thermal conductivity in perpendicular of this axis to the second CNT. So here the heat transfer from CNT A to CNT B is very, very poor, very, very low, and that makes, so we can use this kind of material to design in the thermal management. And the third important point is the thermoelectric potential. So here the CNT, so if you the heat up the CNT, what happens? So that converts the temperature gradient into the electrical energy. And based on that electrical energy, we can use to make the thermoelectric devices. Because CNT converts temperature gradient in the CNT into the electrical gradient, maybe the current or maybe the potential difference, and based on that, we can use in thermoelectric devices. Okay, now we have very important properties of CNT, and that is optical properties here. So let's understand here the optical properties. The CNT has very sharp optical absorption peak, and that peak is called the Van Hoff singularities. And we can explain optical properties of any nanomaterials using quantum confinement. I already explained this effect, quantum confinement. So I already explained this quantum confinement effect on optical properties of the nanomaterials in first class. So here, so based on the different kind of the confinement, maybe you have 3D, maybe you have 2D, 1D, and a 0D confinement. So based on different kind of confinement, we have the different kind of the discrete energy level. So in the bulk, if you have the bulk material, so in that case, so this is kind of the continuous energy. There is no such kind of the discrete energy in the three-dimensional material or bulk material. However, if we have this 2D, maybe 1D, and maybe 0D, so in this case, there is some kind of confinement, and based on that, we have a different kind of this transitions happens. For example, here, CNT is kind of the 1D material. That is this quantum wire and 1D material. And because of this 1D structure, we have here this very sharp energy, that energy peak here, and that is called because of the Van Hoff singularities. So we can explain that confinement of electron in 1D. You might study quantum mechanics or quantum physics. So according to quantum mechanics and quantum physics, that energy level is n square by 8 ma square here, where you have confinement of electron 0 to a. So if you have kind of this confinement of electron in dimension of a here, so this is the confinement of electron distance here, or maybe the kind of the will. And based on this one, so here that energy level depends on the distance of A. And here in for the CNT, so that distance is in confined in the range of, so because one dimension is confined to 1 to 2 nanometer, and because of this confinement, you have the very sharp energy structure, because here the CN, so the diameter of CNT is in the 1 to 2 nanometer, right? And based on the confinement of the electron in the 1 to 2 nanometer, you have the very sharp peak here. And again, we have other kind of materials, the quantum dot. In the quantum dot, we have the discrete energy level from here to there, here to there, and here to there. And that we can explain based on quantum mechanics. So now let's understand transition in CNT. So we have two kinds of CNT. One is metallic CNT and one is the semiconducting CNT. So we have metallic CNT, and maybe we have the semiconducting CNT. So based on this metallic CNT, we understand what is the transitions happen. So in metallic CNT, we have transition from V1. So V1 is the valence band, and the C1 is the first energy level of this conduction band. So there is a transitions from the V1 to C1 happens in this metallic single wall CNT. So this transition from V1 to C1 is called first Van Hoff optical transition. However, in the semiconducting CNT, we have here V1 to C1 energy level is smaller as compared to this metallic V1 to C1, and we have here in the semiconductor we have the different valence band and different conduction band. We have here these are the different valence band and these are the different conduction band. So transition may be possible from V1 to C1, V2 to C2, or maybe here V3 to C3. So here transition may be possible from here, there. And normally here the transition in the semiconducting conducting CNT is from V2 to C2, and that is because of this second Van Hoff optical transition. So here we have two kinds of CNT. One is metallic CNT, second is the semiconducting CNT, and based on these different kind of this properties, we have different transitions happens. In metallic CNT, the energy, so gap from V1 to C1 is higher as compared to the energy difference between in the semiconducting from V1 to C1 and V2 to C2. And if you just combine these energy transition in UV spectroscopy, and we have here the absorption between the energy level. So here we have the S11. So this S11 is because we can say that this S11 is because of the transition in the semiconducting CNT, and this 11 denotes that transition from V1 to V1 to C1. So this one is because of V1 to C1, and S denotes that is semiconducting CNT, and here S22 means that this is the semiconducting kind of the CNT, and the transition is from V2 to the C2, and this so we can write this in the transition of V2 to C2. Valence band second to the valence band conduction band 2, and here M11 corresponds to kind of the metallic CNT, and here 11 corresponds to the energy transition from V1 to C1. So here it turns the V1 to C1. So if you just understand here the energy difference here, so S11 has the energy close to the 1 electron volt, and here S2 has the energy is close to 1.7 electron volt, and here M2 has the energy level is close more is 2.4 electron volt. So based on this kind of the optical properties, we can understand whether we have metallic CNT or maybe we have the conducting semiconducting CNT. And at the same time, we can use this kind of the spectra to quantify this quality of this carbon nanotube we have, whether we have metallic or maybe we have semiconducting CNT. So this is very important information and properties of the CNT. And based on this optical activity of CNT, that CNT shows kind of the photoluminescence and or maybe fluorescence. So what is fluorescence and phosphorescence here? So we can explain this one in terms of light. For example, here if it transitions is happening from V2 to C2, and if that energy difference is and it comes to the C1, and if this comes back to the V1, so what happens? So absorptions happens at E22, that means at higher energy level, right? So here we have the excitation wavelength, so that here the excitation wavelength and emission wavelength. So here emission wavelength from C1 to V1, and that has the lower energy level, and we know E inversely proportional to 1 by lambda. So if you have the higher energy, that means lambda is smaller, and if you have this smaller energy, that means you have the higher lambda. So here the excitation wavelength always should have the lower wavelength, and and this photoluminescence should be at the highest lambda. If you have the higher lambda, then that means energy level is smaller, low, and if you have lower wavelength, we have the higher energy level. So if you want to understand, so if you want to excite that CNT, for example, if you just choose this wavelength and you excite, just put this kind of the curve here. So if you excite at this wavelength 800, so you will get kind of here spectra at 1200 nanometer. And if you excite here, so you have the 1400, if you have the 1600 kind of the wavelength. So we have the different photoluminescence or fluorescence spectra you will get. Suppose you will excite this material at this wavelength 950 or maybe the 1000, so you will get the spectra near to here 1500, 1600 or maybe 1700. So you will get 1500 to the 1700 nanometer, right? So if you excite at 100 nanometer, 1000, you will get the 15 or maybe the 1700 nanometer. So this is about the optical properties. So based on this fluorescence, we can use that CNT in the optoelectronics application like sensor and the imaging devices. And the next important properties is the chemical properties. And we can use CNT in biology or maybe the chemistry based on the surface reactivity of CNT. And here we can fine-tune the properties by the surface modification of the CNT. And we can just modify the CNT. That process is called the functionalization process. And once we functionalize CNT, then we can use either in material, maybe it's drug delivery, sensing technology, maybe we can use in energy conversion, energy storage, conversion application. So there's many applications based on the functionalization process. So now let's understand what are these key steps of the functionalization of CNT. So we have two approaches here. One is the exohedral approach, and the second is endohedral approach. So we have two approaches. So here the exohedral approach means if you functionalize outer layer of the CNT is called the exohedral, and if you just modify the interior surface of CNT is called the endohedral approach. So now let's understand what is exohedral approach. So here in exohedral approach, either we can use covalent bonding, or maybe we have non-covalent bonding between CNT and the functionalizing material. So now let's understand. First is covalent bonding. So we can use covalent bonding here. So we can use in covalent bonding, we can use the direct attachment, or maybe we can use kind of the acid or hydroxy group here. So either we can use here kind of Sidol 1 OOH, or maybe we can use this kind of the functional group on the CNT, and then based on this kind of functional group, we can further modify with the ionic functionalization, or maybe we can convert this acidic group in the amide, or maybe the esters, and using the covalent bonding, or maybe we can use metallic nanoparticle. So we can use this kind of modification if we functionalize with acid or maybe the hydroxy group. And the second is the direct approach here, and in the direct attachment, we can make carbon-carbon bond, so between CNT and functionalizing group here. So here you just understand here the diazotization means you have CNT and you functionalize with the kind of the diazonium salt there. So here we are making the carbon-carbon bond here. Again, if you are interested in a cycloaddition reaction, so you are again making the carbon. Here is the carbon-carbon bond here, carbon-carbon bond maybe you can do the hydrogenation process. You modify the surface of CNT with the fluorination, fluorine, and that is the fluorination process. And maybe you can use the Grignard reagent to make the functionalization of this process system. Maybe we can use electrophilic addition reactions. We can incorporate carbonyl group there, and based on this kind of functionalization, we can use for different applications. So we will learn this kind of functionalization in more detail in next class. Okay, so till now we understand exohedral approach. In this we have used covalent bonding. In covalent bonding, either we can use direct attachment, and maybe we can use acid or the hydroxy group attachment, and based on that we can modify outer surface of CNT. And in other kind of the exohedral approach, we can use either non-covalent bonding. So in non-covalent bonding, here we have the different approaches. So here either we can use surfactant there, maybe we can use the polymers, maybe we can use the metal depositions on the CNT, maybe we can use polymer encapsulation or the kind of polymer absorption. We have CNT, and we can physically absorb either polymers, maybe surfactant, and to modify the surface of CNT. So these are the non-covalent bonding approach. Now let's understand approach about the endohedral approach. That means we are now interested in modification of surface, the inner surface of the CNT. So we can use the encapsulation process. So in encapsulation process, we have CNT here, and we can encapsulate either nanomaterial inside the CNT, or maybe we can use, so here we can use here nanomaterial there inside the CNT, or maybe we can use fullerene inside the CNT, and we can use this kind of the encapsulation for drug delivery application. Drug delivery application. This is a very important aspect in which you can encapsulate your drug inside the CNT and you just deliver that drug to this particular organ tissues, and that is very important application of this kind of material. Now let's understand difference between single wall CNT and multi-wall CNT. So here, single wall CNT has one graphene layer, and if you just roll, that becomes the cylindrical structure, that is the single wall CNT. In multi-wall CNT, we have the concentric graphene tubes, and the diameter is 1 to 2 nanometer in the single wall CNT. However, in the multi-wall CNT, you may have the diameters from 10 to 100 nanometer. And based on this kind of this closing of the CNT, maybe we have the metallic or maybe the semi-conducting kind of CNT. So multiple single wall CNT may be metallic or the semi-conducting CNT. That depends on the chirality, armchair, zigzag, or maybe the chiral structure. And multiple CNTs are generally as metallic in nature. And strength, in terms of the strength, there's really high strength, high Young's modulus. However, in multiple CNT, we have the high strength, and we can use as kind of the reinforcement elements in composite materials. Here in application in single CNT, we can use in nanoelectronics applications because of the semiconducting structures, sensors, and maybe optoelectronics. And multiple CNT we can use in composite conducting fibers, maybe energy storage and field emission applications. So these are the kind of this difference between the single wall CNT and multi-wall CNT. So it is all about CNT, what is CNT, and what are key properties of CNT. So in next class, we will learn the key application of CNT, in which we will learn which kind of the properties we can exploit of CNTs to have application in the different areas. So see you in the next class where we will have discussion on the application of carbon nanotubes. Thank you.